Here's the kind of example problem or problems that you will have to apply the uniform acceleration equations. So you have a heavy object at a construction site 18 meters above a worker's head. It starts to fall. She's going to get harmed if it hits her on the head, even though she has a hard hat. How much time does she have before she has to get out of the way? What I expect you to do for the homework problems coming up and for the next unit test is to draw a diagram that gives you a rough outline of what's going on here. So here's what I would expect. It doesn't have to be great. Some of you are better artists than others, but this could be the building, and these are supposed to be windows, and you have the worker down here, and there's an object up here. I don't know what it is, a hammer or whatever, and then there's 18 meters to the top of her head. Alright, so you draw a little diagram. That's going to count for some points. And then every problem starts off the same. You set up your 5 parameters, your v sub I, your v sub f, a, s, and t, and you fill in the knowns. And it works out that every problem, well, that I'm going to give you is essentially going to have 3 of the unknowns given in the problem, at least for now. And you can always figure out the other 2 given the 4 equations that are set up, that I set up previous to this. So for example, in this case, if the object is starting at the top from rest, the v initial is 0 meters per second. V final we do not know. The object is going to fall, and here's where the interpretation and conceptual part comes in. It's going to be negative 18 meters. It's going to fall 18 meters because the initial starting spot is going to be our 0 location. We'll talk more about that as time goes on. And this is always going to be negative 9.8 meters per second squared. If you want to use 9.81, you may. But once you know 3 of the 5 of these variables, there's always one of the equations that can be used, or a combination of equations that can be used to figure out the other 2. What we're looking for here is time, but it may make more sense to find the final velocity before the time, not necessarily. So once you have this filled in, you will need to find one or more of the equations, and sometimes there's multiple ways of doing the problem, to determine the other 2 missing variables. In this case, I think the third equation, you need to be looking at that box with the 4 equations. You can have that printed up off to the side. I'll give you those on the next test. But I know from doing these enough that the third equation there is one that's going to work really well to figure out. So let me see if I can move this out of the way a little bit. Hopefully I can bring that back. But the third equation works well here. That's S equals v sub I times t plus 1/2 at squared, where s in this case is negative 18 equals, and v sub I is 0, so I'm going to have 0 times t. That'll cancel out, so I don't need to write that because v sub I is 0 times t plus the 1/2 at squared. So it's going to end up with 0 here plus 1/2 times negative 9.8 times t squared. If you do the math here, t works out to be, and you multiply both sides by 2 and then divide by 9.8. So after you multiply by 2 divided by 9.8, it becomes out positive, and then you take the square root so that t equals 1.9 seconds. You don't need to show me all the algebra. What I prefer you to show me is your equation that you're using here, this equation I'm circling. Plug in the numbers and then give me the answer. You don't need to show me all the algebra. So the answer is 1.9 seconds. I went down to 2 sig figs. If you go to 3 sig figs, that's fine as well. Even if you switch back and forth, even though you shouldn't, between 2 and 3 sig figs, that's okay. It's like 1.91 seconds. Alright, so this is how much time she has before the thing hits her in her head. You could also, if the problem also said, you know, what's the final velocity, or what's the velocity with which it would have hit her in the head, you could continue on and use one of the other equations. I think almost any other one will now work. For example, the first one, which is v sub f equals v sub I plus at. So v sub f is going to equal your v sub I, which is 0, plus negative 9.8 times your time, 1.9. So the final velocity is negative 18.6 meters per second, or negative 19 meters per second. The negative indicating that the object is traveling in a negative direction. Let me show you one more example problem. So the process will be the same again as was the last time. We're going to draw a picture. Somebody's on the ground, they have a baseball, they're going to throw the baseball straight up next to a building where there's an open window with somebody who wants to catch the baseball, easily catch the baseball. So the baseball's going to go to the top, and it kind of stops at that top peak at an instant, at 8.4 meters above the ground. Now, a couple of assumptions, or at least one assumption we have to make, is that the 8.4 meters is from where the ball is released. That's the implication here. If you're ever unsure of that, you can ask me about it, but we need to know how far it is from where the ball is released until it's caught. So here's a little diagram. I guess it's the same diagram as before. Switch to red. Got your windows, third floor. I don't know, there's a person here with their hand out. Not a very good picture of their hands, but somebody down here, and the baseball is going to go up, 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 and it's going to be caught right there at that spot. So, little diagram. This is what we assume is the 8.4 meters. Otherwise, you can't do the problem. That's 8.4 meters. All right, so we have V sub I, V sub F, A, S, and T. So every problem is going to start off like this. You have the little diagram. You have your 5 variables. And here's the troubling part about this one, and that is the release speed. We're not talking about the person holding it in their hand. The person has thrown the ball, so the ball's out of the person's hand. So the initial velocity of the ball is not 0 in this case. They're not dropping it, they're throwing it. So the ball is no longer in the hand. We're talking about the velocity of the ball as it's coming out of the hand. The ball is going to go up, 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 and at the top it stops for an instant. So the final velocity is now 0 meters per second. But like the last problem, all the problems we're going to be doing here for the next few days, this is the acceleration due to gravity, which is going to be negative 9.8. Always negative 9.8 meters per second squared. This ball now, your initial spot is your 0 displacement. This ball is going to have a positive 8.4 meters displacement. It's going up from the release spot. So we always call our release spot, or we can call any spot our 0 spot, but the best spot usually to pick is your 0 displacement, is where the problem starts. Point A is where the thrower's hand is. So now we have our 3 variables. Once again, now the rest of this problem, all the physics is done. The rest is algebra, finding the right equation. We're trying to find V sub I. And I think the 4th equation, which is V sub F squared equals V sub I squared plus 2AS, once again, to be looking at these equations, can give us the initial velocity if you plug in the others. Let me move this out of the way. Try to move this out of the way. Plug in the numbers. So V sub F is going to be 0, squared is 0. We're looking for V sub I plus 2 times negative 9.8 times positive 8.4. So if you move things around, it will end up with, say, if you move the V sub I over, you get negative V sub I squared equals some negative number. So the negatives will cancel out eventually here because there will be negatives on both sides. This comes out to be 164.6 or 165, negative 165. So divide both sides by negative 1. You can have V sub I is going to be the square root of 165. So let me move this up a little bit. So on the square root of 165 is like 12.8, or round off to 2 sig figs, it's 13. So the thrower has to throw the ball at 13 meters per second. So the ball goes up and just comes to a stop at that 8.4 meter mark, and the person can just grab the ball and haul it back inside. Once again, you could use another one of the equations to figure out how much time that would take for the ball to get there. Tomorrow we will practice some more of these problems in class.